Okay, yep, we'll get going. So, good morning, everyone. Thanks for joining the workshop. It's exciting to have this opportunity to talk about CanESM. And so, yeah, pretty much the rest of today, it'll be myself and colleagues from Environment Canada describing aspects of CanESM. And so I just want to really thank all my colleagues for taking the time out of their schedules to come and do this exercise. And yeah, so I'm going to kick off with just describing CanESM as a collaborative model. Okay, so basically just talking about what CanESM is, its history, where we're going with it, how it's composed and developed, talking a little bit about it generally as a collaborative model, and then a bit more specifically about what we've implemented for CP4C on those DRAC machines and some of the work that we've done there. So Paul alluded to this, but CanESM has a long history going back even maybe 50 years from original atmospheric models that were developed, then over time increasing in complexity to coupled models, and ending today with a model that we have kind of used for scientific applications, which is CanESM 5. And along with the model development, there's been application of this model really prominently in the international community via the coupled model intercomparison project, feeding into IPCC assessment reports. It's been used in a lot of other things too, though, for example, Canadian climate assessments and WMO scientific assessments of ozone depletion. So the model itself is very well known and vetted in the international community. And so, but today we'll be focusing on CanESM 5 and the results that were contributed to the 6th assessment report of the IPCC. So CanESM 5 is a coupled atmosphere-ocean general circulation model. It includes a prognostic carbon cycle, and the model itself is predominantly written in Fortran. So it contains these components: CanAM atmosphere, an ocean model based on NEMO, and then there's biogeochemistry in the land and ocean. There's also sea ice, lakes, and there's a whole set of environment and tools which kind of underlies this model, which allows you to use it on high performance computers. So when you put all of these things together, the full coupled model CanESM becomes much more than just the sum of its parts. And so for people that might be used to using individual models like an ocean model offline or a land surface scheme just offline, once you put these things together, it does become kind of a different beast. They all have to interact happily with each other and produce some kind of a reasonable climate. And it's a little bit of a different kettle of fish there. So in terms of the lineage of CanESM, because this AGCM component, the land surface component, and that ocean biogeochemistry have all been fully developed at CCCMA, and we've also taken a community model for the ocean NEMO, but customized it. Within the international climate modeling community, CanESM is quite unique and has this unique lineage. So it really is kind of like an independent model. So there's a lot of models that are used in international climate science that are just like very similar copies of like CESM, for example, but CanESM is quite distinct in its lineage, so it adds some value there. What we focused on for this model is having something that's really physically well reasoned. It's got coarse resolution, T63, about 300 kilometers in the atmosphere and about 1 degree or 100 kilometers in the ocean. But we have something that's very computationally efficient for a coupled model. So if you look at the resolution versus the expense in core hours per simulated year for all the CMIP models in blue, CanESM is the model down here in red. So yeah, we are at the lower end of the resolution spectrum of CMIP 6, but it's very, very affordable to run the model. And that allows you to do a lot of science. For example, we've done a lot of large ensembles using that. So we've configured that model to run about 100 different CMIP6 experiments, plus many custom applications at CCCMA. As I'll say later, only a fraction of those are available to CP4C, but that's the breadth that the model has been used for. We have a very extensive diagnostics pipeline to evaluate the model and to meet that CMIP6 data request, which is very extensive. And then, as I mentioned, this infrastructure to enable people to use the model on high-performance computers. So all of this is described in a GMD special issue on CanESM 5. Okay, so when we put all of this together, we get something like this. So one of these is ERA 5 reanalysis, basically observations, and one of these is CanESM 5, and you're looking at the surface air temperature and sea ice fields in the model. So, you get an interactive simulation of the climate that looks very physically plausible. most people know this, but I think there's some new kind of people in the audience to Earth system modeling. So I'm just kind of giving an overview of the type of results that these ESMs will produce. Of course, there's hundreds of other fields and variables that we could look at, but just here picking out a prominent one. So this is really just kind of reflecting on what I was saying. The top is just showing all the different MIPS that we contributed to. And as Paul's mentioned, CCCMA conducted, I think, over 300,000 years of simulation for CMIP6. We made a huge submission there. It was all documented in this GMD paper, but actually there's more generally a GMD special issue, which contains several papers describing different aspects of the model. And so what we have are actually two versions that we've now submitted to CMIP6. CanESM 5 was the original one, and then we followed that up with CanESM 5.1. That's also got a formal CMIP6 submission. So both of these are well known and stable, and they are the versions of the model which are available for scientific applications, and that we'll talk about more today. So I just want to talk about CMIP, well, CanESM in the context of the CMIP model. So this is a diagram from the Chapter 3 of the IPC6 assessment, and it's a so-called portrait diagram where basically along the y-axis is many different variables, and then on the x-axis is many different models, all the models that participated in these different phases of CMIP. And the colors give you an indication of how well those models are performing in some relative sense, but blue is better and red is worse. And I've put orange boxes around the models from CCCMA, basically CanESM. And so what we can see is that as we go through CMIP generations, the colors in these orange boxes get more blue. So in other words, the climate of the model relative to observations has improved over time. So the model's been getting better. So model development is working, which is good. But there's another thing that I want to point out in this diagram, that even though CanESM did have that very low resolution, if you look across all the CMIP6 models, you can see some models that have a lot of red in them. They're standing out as not being super good relatively to observations. But CanESM does not have that. You know, we're maybe not the best model in CMIP6, but we're kind of in the pack. So despite having this very coarse resolution, we actually get a pretty good climate in the model. And that's because we have this very intense focus on having coherent physics and doing the coupling carefully. And so, yeah, we focused on that physical part of it in this model, as opposed to just like trying to solve all problems via resolution. And that actually does produce good results, and it allows you to do some good science. So one feature in particular of this model is that out of all the CMIP6 models, CanESM 5 has the highest equilibrium climate sensitivity, or you could phrase that as transient climate response or historical climate warming. So we can see in the figures here from Michael Sigmund's paper that say observed warming is in this gray line, and CanESM 5 and 5.1, what we call the P1 variant, have warming that's quite a bit larger than the observations. And if we can look at that in a abrupt 4 times CO2 context and see that they have quite a lot of warming, we do have another realization, which is exactly the same physical model, but just with parameters retuned, and you can actually get a significantly lower climate sensitivity, more like around 4 Kelvin. So we have a few variants there with different tunings, and relative to previous versions of this model, the high climate sensitivity really arises because of improvements. So improvements in the ocean model that produced a different SST pattern, and improvements to the cloud physics scheme, which led to different cloud physics response. Again, a lot of this is described either in Michael's paper or in work in that GMD special issue. Okay, so as we go forward, basically we've had CanESM 5, we've developed CanESM 5.1. Both of these are available to CP4C users. We're currently working on CanESM 5.2 internally, but that is not released yet for scientific applications. And in parallel, we're working on CanESM 6, which will be quite a different model based on a different dynamical core in the atmosphere, the gem dynamical core, but this isn't expected for another year to year and a half. We also have a lot of other activity on regional modeling and applications at CCCMA, but today we're just really focused in this top kind of panel of activity. Okay, so let's talk about CanESM and open science. So a few years ago, we put together a CCCMA strategic plan where we basically committed to proceeding in this kind of more open way, and that had several components. One of them is a fully open source code. So we publish the code publicly on gitlab.com, and that's updated every night. So our latest code is mirrored there for the kind of operational version of the model. We have extensive public user guides and developer guidelines, as well as those scientific description papers, which we try to make all open access. We have a commitment to maintain platform portability of the modeling system. So when we're writing either infrastructure or parts of the model, we really are trying to be strict about not, customizing them to only work on one machine, but making them portable. So, even in open source code, it doesn't matter if the code's open source if the source code can't be compiled or used on different machines. So these things are actually different. We're also trying to be good about making open publication of our forcing data sets that those are the inputs that the model needs to run. And we see this as all being kind of part of this virtuous kind of cycle where, we do this work, develop this technical infrastructure and these systems that improves the development of the model and the physical processes. It allows new, highly qualified personnel to be trained and, for people to apply this externally and learn new things about the model, even if they don't develop new features. Just learning about properties of the model is something that we see as, a benefit that Environment Canada would gain out of this kind of collaboration. And so all of this stuff is done just kind of under our open government mandate. It's not really specific or exclusive to CP4C. Anyone can go and download this source code basically anywhere in the world. And we don't in CCCMA really have a mandate to support individual machines, although we have done that kind of for CP4C just kind of to try and get things going, but it's not really part of our mandate. So for collaborative platform for CanESM in particular, I would say we see this as kind of a value added effort on top of Open CanESM, and it's run by the community in collaboration with ECCC. And so, what we've done is a lot of technical work and policy work and other kinds of things to try and get this off the ground, but that's basically too much to read. So what we've done is we've given money, plan to give more money. We've provided a bunch of in-kind staff time, both kind of scientifically and technically, and we've established practically this validated port of CanESM on the Niagara machine of DRAC for targeted versions and experiments, and provided guidance on how to run it. So just to quickly touch on that, on Niagara, what we have is two supported models, CanESM 5.0 and 5.1, and we would really suggest using 5.1. That's the one that's kind of got more comprehensive support, I would say. There's certain experiments that have been put across, which is essentially right now CMIP6 DEC plus some SSPs. We've prioritized putting on experiments that people told us they were going to use, so additional ones can relatively easily be moved across. But these are the ones that are available at this moment. We've validated the climate, so there's a technical report that published last year on validating that. And this figure is just one kind of example of that. So this is surface air temperature in SSP 370, the Environment Canada run, and then the run done on Niagara. And so, of course, the bit pattern is not exactly the same. It's a different realization of the climate, but the climate change is exactly the same, and the base climate is the same. And we've done a lot of other extensive analysis to convince ourselves that the climate of the model is the same, and that includes work kind of in collaboration with some students within CP4C. Okay, so not only is the model there and functional, but we've also done a lot of work on the data pipeline, and we're now producing this fully so-called CMORized net CDF data. So I think this is something really special. Like even if you use CESM, you're not getting CMORized data out of it. So we're really providing the final data product in a format that would be familiar to many users because it's that CMIP6 standard. We've also worked with some CP4C students to really try and get a good performance of the model. So we're getting currently 17 simulated years per wall clock day, and using about 340 core hours per simulated year in the default configuration. So this is more or less comparable to our performance internally in Environment Canada. So we're doing pretty well on how efficiently the model runs on DRAC. So in addition to that, we have this wiki on the GitLab for the CP4C project, and we have various things like technical reports, that's the validation of climate, partly is in there. We've got a reference run tables so that people can compare what any runs that they do relative to known references. We have these basically copy and paste quick start guides where people can click on that and just see a set of like a recipe how to run the model. and then also more extensive user and developer guidelines in general for CanESM. And we'll go through a lot of these things much more in depth in the walkthrough tomorrow. Okay, so in terms of collaborative CanESM, like what do we really actually mean by collaboration, particularly in CP4C? So I think we mean here that model application and especially development are done in collaboration with ECCC scientists according to the CP4C guidelines that Paul mentioned. It's not, we're not just saying this is like basically a community model in the same way that CESM is, but it's really envisaged to be collaborative. So scientists and working groups at CCMA are, of course, individuals. We can't compel them to do anything like collaborate or to not. So it's their prerogative to choose whether to collaborate. But if there is an agreement to collaborate with someone external to ECCC, then CP4C really is providing a useful tool to enable that collaborative work. But it doesn't, the existence of the tool does not infer an obligation to collaborate, I guess I would say, on any individual or working group. They have to agree that it's, you know, beneficial to all parties. So then application of CanESM, I think in this framework, would include a degree of kind of consultation and review following the CP4C guidelines to help ensure that people can use the model efficiently and that they're doing it in a scientifically valid way. And then finally, just in terms of the development, I think that's something that has to really happen in close consultation with CCCMA if people want any of the technology or scientific parameterizations, et cetera, that they develop to come back into the model. It needs to be done by starting with a conversation early with the relevant working group, and whatever work is done will be tested and processed with exactly the same standards and everything else that's any internal development at CCCMA has done. And this is largely documented in the developer guide. Okay, so yeah, about 4 or 5 years ago, we kind of originally came up with this list of 10 things that we needed for elements of collaborative CanESM, and a lot of them were kind of outstanding features. And I just, several years later, I think we have done really well, and most of the problems that we originally identified have either been resolved or we kind of have pretty good workarounds in place that we're still developing. So yeah, I think we have actually come a long way on the usability of this over the last 4 years, and so we're doing pretty well. So yeah, just to conclude, CanESM 5.0 and 5.1 are well-known models that are thoroughly evaluated in CMIP 6. They have open source code. We've got a limited number of experiments that can be run basically with copy and paste ease on Niagara right now. We are committed at CCCMA to try and maintain this open modeling system. And there's many individual scientists and groups that are interested in collaborating using this tool that's now available. As we move forward and hopefully CP4C gets additional resources, we anticipate that project will take over the specific support on DRAC machines and will focus on just providing that collaborative system. But yeah, that is all that I had to say today. Thank you very much.
Thank you, Neil. That was great. Does anyone have any questions before we move on to Jason Cole? Yeah, Paul.
Questions. Just a quick comment that the last, first of all, Neil, thanks very much, and it's been a tremendous amount of work that you put in yourself, and now your colleagues are really putting in a lot, and so I want to acknowledge that huge amount of support you've provided already. I just also wanted to say that we did a survey 3 years ago now on what the needs were, and there you talked about the interest internally at CCCMA in collaboration, and we also found this. In fact, some respondents from our survey were from inside ECTC, and others outside were saying we would like to collaborate. And so now we're starting to see how much effort it takes to overcome barriers, but there's a finite number of barriers. They're not infinite in number, and so I think we're going to start to see the outcomes here. And the output, the summarization is a key part of that. Like that's really, really one of the more important steps. And that was, I know, that was a really major effort. So your list was too long to read. I think that really means something. right? It wasn't boring. Every bullet point on your list was actually person effort. And so we need to document that. And so we'll keep that in the archive of all the effort. So I know it's a bunch of comments, but just to say that I really appreciate what, all the messages that you provided today.